We are very glad to have you here now. Stephen made his PhD at Stanford University, and he was working several years in Silicon Valley in the electronic industry. Tested later various institutes, various universities or institutes. And since 3 months he is with the SIT, and we are very eager to hear something about microreactor channels. Please, Ron.
Okay, thank you. Thank you for that introduction. Yes, so my industrial background is really in the electronic materials area and in microfabrication. But my undergraduate major was chemical engineering, and so then about 3 years ago, when I had the opportunity to go to the Institute for Micromanufacturing in Louisiana, I was able to sort of combine these two interests, and in this very exciting area, I think, of miniaturization of tools for chemical engineers. And so I made sure to put catalytic in the title, given the name of your group here. But really what we do is mostly catalytic reactors. And so, again, I am at Stevens Institute of Technology, which is in Hoboken, New Jersey, right adjacent to Manhattan. And so we have a very good setting for not just being near the so-called center of the universe, but also being near the greatest concentration of pharmaceutical companies in the world, and a number of chemical companies and high-tech and fuel cell companies, all kinds of opportunities for collaboration. So I want to just, the spirit of this talk is introductory, and I think microreactors, meaning microfabricated, microscale reactors, have gained greater and greater publicity in the chemical and chemical engineering world. But I think a lot of people are still unfamiliar with what they actually look like and what they're really all about. So again, this is intended to be an introductory kind of talk. This is just a motivation for miniaturization. When we look at Moore's law, this is the law that has produced the wonderful machine that's sitting on your desktop and the little box in your pocket that enables you to talk to anybody around the world. And it's really an exponential kind of increase in complexity that's led to extremely high density, and not just in microelectronics, though that's what we're most familiar with, is computer chips and microelectronic chips. But then in the last 10 or so years, getting into this area of microelectromechanical systems, which initially were miniature mechanical systems, things like this gear here and little pinchers and that kind of thing. But generically now, MEMS really refers to a whole array of miniature devices that are formed by microfabrication techniques that could be used in the optical communications world, or that could be used in this projector may have a digital micro mirror array in it, very likely, most of the new ones do. And then also can be applied to chemical systems. And so that's the question, that's the proposition here. Can we take something that we're used to operating as some kind of chemical process in kind of a macro fashion and reduce it, or in somehow translate it, not necessarily reduce that whole capability that you see there, but somehow translate it into a device that is very small, and does it, and in doing this, if we're going to do this, what advantage do we gain? And of course, we should only do that there are specific advantages to be gained. And so that's the whole theory, that these microchemical systems have specific advantages over their macroscale counterparts. So this is kind of the outline of the talk. What is a microreactor? What do they look like? Let's look at some pictures of some that various groups have produced. Why? A little bit more on the benefits of miniaturization. And then I want to give you some examples from our work of how we actually have made these reactors and characterize them, some reaction results, and then finally conclusions at the end. Okay, so what are they? So the word microreactor for chemical engineers and catalysis people, up until maybe 4 or 5 years ago, and even in many circles, maybe most circles, microreactor means a little tube that's packed with catalyst we're going to characterize and then use that same catalyst in a scaled-up system. And so that's what I refer to as your mother's microreactor. And we're not talking about that. It's not your mother's microreactor. And the key aspect of it is that the critical dimension, the most critical dimension of flow in the system is much smaller than even that microreactor that you think of as pretty small. And so here's some examples. These are both from a German group that's one of the leading groups. And you can see here, this is a system that's based on, or that is composed of several different unit operations. Here's a mixer, micromixer, and a reactor here. And this is a heat exchanger here. And you can see how this is all sort of integrated into a size that makes the kind of conventional looking swage lock type fittings there large in comparison